Okay, so today we're going to be talking about operating systems that are fit for Internet of Things applications. And we're going to go through some of the details that these operating systems actually have to implement to be suited for IoT applications. It's a specific area and there are particularities for them. Mostly given by the types of devices that actually run in IoT, also the constraints that IoT applications usually have, be it size, be it power consumption, be it processing power, and so on. And afterwards, we're going to talk about I think 4 or 5 major operating systems that are used right now in IoT systems. Just briefly gonna go over them, each one with its particularities. And after we have done this comparison, we will do a brief demo of one of the operating systems that I'm presenting here, namely Contiki OS. So it's gonna be a very hands-on session for today. Let's briefly go through some of the particularities for IoT applications. As you know, we are talking about internet connected objects, RFIDs, sensors, actuators, different types of instruments, appliances. They all have their own particularities, but in general, for an IoT device to actually be an IoT device, it needs to be connected to some sort of a network, ideally the internet. So you will have these devices that do communication between them. They establish a network. It might be an ad hoc network, multi-hop, or it might be a single hop network towards a base or a collector. And then they do some local computing or computing done in the cloud. Uh, Given the fact that the IoT concept has been developing in the past 20 years or so, it adopted easily new standards. So it's more readily compatible with IPv6, for example, rather than IPv4. That's one of the reasons. And of course, another reason is that given the sheer number of IoT devices that are running in the world right now, IPv4 is not suitable because of the address space, very limited address space that has already been exhausted. Now, mainly IoT applications, we say they are powered by these sensor nodes or modes. These are low-cost devices, usually very small in size and very power efficient. You would need such a device in order for an application such as, I don't know, battery-powered applications or remote sensing applications, or some sort of home automation application that you don't really want to interact very often with that device, maybe apart from changing its batteries once every couple of years. And otherwise, it just does its job, and it actually measures or actuates some of the parameters in its environment. Another interesting factor for IoT applications is the real-time guarantee. So more than ever, these applications are deeply embedded within their environment. They are reacting to stimuli in their environment, so they need to be real-time, and the operating systems that actually run on them need to have a real-time guarantee. So we're going to be talking about 4 operating systems in the next slides. Each one of them is a real-time operating system in itself. Now, as a standards for IoT, I just wanted to make a brief comparison between, let's say, the standards that are used for computers, so PCs and desktops and so on, at each layer of the stack, the protocol stacks, and then do a brief comparison with what we are seeing in IoT in IoT land, so to speak. So we have different protocols. If, for example, for computer networks, we have HTTP and FTP as high-level protocols. Here, most of the devices do not employ FTP or HTTP due to size and processing power constraints limitations. What you're going to see more often is going to be CoAP as an application layer protocol. Constrained Application Protocol, as its name stands for. I think we have briefly touched upon CoAP in a previous lecture. Again, at the transport layer, you might have TCP, UDP, ICMP in a regular computer network. Here, usually the communication is stateless, so we don't have devices that have very extensive capabilities for computing and memory and so on. Most often you have devices that actually go to sleep very often, so they transition to a very low power state where they lose connectivity within the network. So a stateless protocol would be better suited, such as UDP, for example. IPv6 again is used very often for IoT applications. I named one of the reasons in the previous slide. Most IoT applications right now use IPv6 as an addressing scheme for their applications. But IPv6 is not fully implemented most of the time. So you've got this translation layer called 6LoWPAN that actually achieves the role of protocol right now for IPv6 instead of IPv6 or IPv4 in a regular computer network. 6LoWPAN actually is widely employed also in IoT applications. It's a very lightweight translation layer protocol. And at the base of it all, we have, instead of 802.11 or 802.3 standards, we have 802.15.4 as a MAC layer and as a physical layer, which we have talked a lot in the previous lectures. So there are some particularities for IoT applications, and an operating system that actually employs IoT devices usually implements applications and different programs and protocols from this stack on the right here. So what does IoT demand in particular? Well, usually it demands low power, low cost, and low memory footprint. These are three main characteristics for an IoT device. Not all of them, of course, but the vast majority of IoT applications require either one or all three of them. So you are deeply constrained in terms of how much battery you can actually consume with every, I don't know, every communication that you are making. You are also deeply constrained about how much processing power you are putting on board the device, because the cost element of this is very important here. So you would need to actually deploy maybe hundreds of thousands of these devices, and then cost actually needs to scale very well. So we're talking about devices that don't cost more than a few dollars. Of course, you cannot squeeze a lot of processing power out of that production cost. Again, cost is dictating actually the memory footprint as well. So memory costs as well. So you're not going to have gigabytes very often of memory available for an IoT device. Most likely you're going to have kilobytes, or the best case megabytes of memory to actually run your application. And this is both RAM and flash or ROM, where you are storing your program. These actually dictate a lot of how the operating systems that we're going to talk about in the next slides are structured. So we're not seeing operating systems that, let's say, are common to PCs or desktops, where you have a very friendly user interface, where you have a lot of applications and a lot of protocols already implemented. And you have a very generous memory footprint. No, it's usually very constrained operations, very low footprints for the operating systems, and usually it's a high degree of modularity, so you can easily add or remove different drivers, different protocols from the OS stack. So On the communication side, you should have a provision for IPv6. Not all of them, of course, have it, but the majority of applications use some sort of addressing scheme when communicating with their nodes. You can basically write your own communication protocol, but in general, if you want to be standard compliant, you would have a provision for IPv6. And with the caveat that you're not going to use the full IPv6 implementation most of the times because memory footprint and processing power, and you're going to use the 6LoWPAN adaptation layer to actually make things happen. Whenever you are dealing with these devices, they usually employ some sort of radio transceiver to communicate with other devices and or a gateway. These radio transceivers, they are, again, low cost, so they do not employ a lot of error correction. They usually do not have a lot of transmission power, so the range of the radio transceiver is not great. And from what we saw in previous lectures, they use kind of the same frequency spectrum as other more established protocols such as Wi-Fi, so 802.11, which means that you're going to have a lot of noise when communicating with these devices. You're going to have a lot of collisions. You're going to have channels which are very much jammed with other information from other devices, which might coexist with the IoT application. What that does, of course, is you're going to have a lousy network. So a network that is prone to actually not delivering packets or prone to errors when delivering packets. And most of the time, what your error correction capabilities are very limited. So retransmission is very frequent employed skill whenever you want to actually send a packet that has been corrupted. Again, low power is key here. You'd like to have a radio transceiver that does its job and does its job without actually taking up a lot of energy in the process. So very low power usually means very low data rates or very small transmission ranges in the terms of meters or tens of meters for most IoT applications. Usually there are new and lightweight application layer protocols, such as CoAP here, which, unlike HTTP, they have their own particularities, but some of the operating systems also provide support for HTTP as well. We're going to see in the demo, for example, way to connect through a simple web browser to one of the nodes that we're going to simulate in the network, and it's done through HTTP. For IPv6, you have to have header compression against 802.15.4 because 802.15.4 MTU is not compatible with the MTU for IPv6. So basically what you're going to be doing is compressing header information data from IPv6 to make it work on 802.15.4 MAC networks. Now, when we are designing such operating systems for these very constrained devices, we're going to have some particularities. And these particularities are actually dictated by different kernel structures. So for example, you can have a very monolithic kernel structure. You don't have modularity, but this one becomes very complex once you exceed a certain limit in the OS size. Or you can have a layered approach where you segregate basically the kernel mode and the user mode. But given the fact that most of these processors that are running these operating systems do not have enough facilities for virtualization, do not have memory management units, this kernel mode versus user mode distinction is purely academical. I mean, you can easily write a program that accesses everything in this processor, memory locations everywhere. So there's very little memory protection employed by these operating systems. You are pretty much the master of the entire system. Or microkernels. Again, microkernels is a different paradigm of kernel organization for an operating system, and this is preferred for a limited set of tools that run in kernel mode, and most other drivers and modules, they run in user mode. So microkernel as a design as a design philosophy is adopted usually by operating systems that have not gone into the mainstream very much, but you can actually see this organization in some of the operating systems that we're going to present. Now, on the programming side of things, the model that is adopted by most operating systems here is that you're not going to have any memory segmentation, any memory protection at all. So you're going to be able to access the entire memory of the system, which of course comes with its own caveats. But most of the time we're talking about very limited processing power, very limited processors. So it might be even 8-bit architectures that we are dealing with. So there's imagine you are doing programming on a device that has probably the same capabilities as I don't know, maybe 386 Intel processor or 486 Intel processor back in the day. So you have, although this happens, of course, you have some facilities. For example, you can run separate threads, and these are concurrently executed by the operating system. You can have some sort of scheduling scheme for these threads, and you can have your own memory stack allocated, albeit that memory stack is very little. So we're probably dealing with systems that have very little footprints in RAM, maybe hundreds of kilobytes. So you're not going to have a lot of local stack available to you to actually do a lot of implementation. So usually it's a challenge to actually develop applications, complex applications with these operating systems, which makes it the more interesting, in my opinion. So the main operating systems that we are going to be talking about are these. So we're going to be talking about TinyOS, Contiki, RIOT, and NuttX as main operating systems that are used right now for different IoT applications. Now, TinyOS is a monolithic kernel, I was mentioning before. You can actually find this operating system if you go to the link here, tinyos.net. It doesn't use, let's say, a very well-known programming language. It uses a variant of C called NES-C, and it provides algorithms, protocol stacks, device drivers, file systems, and also serial shell that you can use to actually interact with the sensor node or the device that runs TinyOS. It's been very popular, especially at the beginning of, let's say, the 2000s in developing IoT applications. And it's been one of the first, actually, operating systems that has been developed for IoT applications, even before IoT was a thing, so to speak. So was actually an established name for these applications. We were talking about sensor nodes back then, wireless sensor networks, and TinyOS was the operating system to actually implement these. Unfortunately, it's not been maintained anymore, so it stopped its support. It's not extensively maintained, and you can still develop applications in it, but they're not going to be, let's say, very competitive with the other operating systems that are running right now. Another one, which we're going to actually talk about a lot today, and we're going to have a demo, is called Contiki OS. This one's been implementing as a research operating system initially. So it has its origins at university level. Swedish Academy of Science actually has implemented this, if I'm not mistaken. And also, TinyOS was the same thing. It started as an experimental operating system for academia, mostly built for research, and probably that's why it's that hasn't found its way into some commercial applications, and this is why it was not maintained. Now, Contiki, on the other hand, has found its way to some commercial applications, and you can still develop in Contiki, and it's rather popular to some IoT applications. It uses also C as a main programming language. It does have some partial C++ support. The architecture usually is very layered for Contiki. It's not a monolithic kernel. But it provides the same abstractions basically. So device drivers, it provides a communication layer, sensor data handling, services, and so on. You can have different timers, for example, processes being declared, threads that run in a pseudo-parallel fashion, and so on. Also, you have a IP stack. It's called micro IP stack that you can actually use to build communication between your Contiki devices, device drivers, proto-threading system. This one is really particular to Contiki, and it allows you to do some sort of multitasking. Although the scheduler, from what I remember, it's a collaborative a multitasking scheme in which each thread runs its own context and then yields to another thread, the processor. So proto-thread, simple, lightweight, multi-threading system. You have a stackless implementation for them. So this is Contiki. Then RIOT. This is a microkernel approach for building an operating system, and you can find it here, riotos.org. Again, it's an operating system that has seen some commercial development, so that's why it's maintained. The scheduler is stickless, so whenever you want to actually switch your operating system to idle mode, you can switch to an idle thread. It is designed that the kernel functions are scheduled under low clock speed, so you can actually have some low power functionality there. It's fully supporting C and C++. And partial support for POSIX is also ensured, which is very interesting because you might, have an ease of development after developing, Unix type applications. You have full support for different protocols and adaptation layers, IPv6, TCP, UDP, etc. So it's very modular, and it has usually devices that can be very low power, very low memory footprint. The entire footprint of the operating system after compilation could be a few hundred bytes of RAM and ROM. So very, very slim in terms of how much memory footprint it has. And it supports multi-threading and real-time. So it has a lot of facilities, zero interrupt, zero latency interrupt handlers, minimum context switching times that you can actually use to achieve a real-time, actual real-time guarantee for your applications. Okay, the other one is NuttX. NuttX has been created by Gregory Nutt. That's why the name is NuttX. The first release was in February 2007. It's a very interesting operating system because it supports devices that are very wide ranged. So from 8-bit architectures such as AVR architectures to full-fledged 32-bit ones, ARM processors, Cortex-M, for example, and you can even run it on x86 devices. So it's It's very versatile in terms of supporting microcontrollers or microprocessors. It has a huge, actually, number of devices which actually can run NuttX. Usually it's released under a BSD license, and you can actually find the operating system here. It's part of the Apache project right now, so nutx.apache.org. Again, just like RIOT, just like Contiki, it has a very small footprint, so it's suitable to actually be deployed in devices that don't have a lot of memory. And it's very customizable. You can actually add modules, drivers, protocols, and so on, or remove them. The interesting fact about this one is that it's inspired from Linux and Unix. So it's got a lot of the facilities that, let's say, a Unix device has. And also it's POSIX compliant, which is, again, a big plus. You can have a scheduler which is running on this one. It can be a preemptive scheduler or a collaborative one, I think. Again, file system support, very important. You can have a variety of file systems that can be added to it. Loadable kernel modules, just like the modules that can be loaded in Linux and Unix. Support for multiprocessing, scheduling, tickless operation, and terminals that can be actually employed to build applications. Now, if we put this into a table, these are the, let's say, three operating systems that we've discussed right now: TinyOS, ContikiOS, and RIOT. Now, in terms of availability, support, programming, and so on, these are the, let's say, main particularities for these operating systems. You can see that usually the footprint in RAM and ROM is very tiny. So we're talking about kilobits or memory for each of them. So this is actually holds true for all the operating systems that we've gone through so far. But there are, mainly differences in the programming style for each of them. So NESC, for example, for TinyOS doesn't make it very appealing to programming because you'd have to learn some, let's say, new programming ideas for NESC. That it's not that different from the regular C that we're using. But of course, contiguous, RIOTOS, NuttX are very well supported, and right now they are being deployed in a lot of IoT applications. And again, it makes a very big difference where you're having true multi-threading operating system, and you have true modularity, so you can easily swap components or add components and so on. So again, this is a different comparison here in terms of memory footprint, in terms of supporting different programming languages, multi-threading, memory management unit, with or without, real-time operating, and modularity. So it's a good comparison. Now, questions so far? Okay, so we're going to move forward with a contiguous demo. We're going to go through a simple hello world example, and we're going to build on that to actually add some more facilities to it, see how the event system is actually working in Contiki, and move to a simple LED blinking serial shell example. And then we're going to finish off with a full network stack implementation application with a border router that actually uses IPv6 to connect nodes, different nodes that are establishing an ad hoc multi-hop network, and then connect to the internet and see the data that the network is actually collecting through a web browser. So this is what we're going to be talking about next. Now, I've put some references here for what we've talked about in this lecture, so feel free to actually consult these at any time. And let's briefly break right now so I can actually start up the virtual machine to run Contiki. So let's resume in I don't know, maybe 5 minutes.